So in the last video, we looked at what happens when soda fizzes, and we focused mostly on the macroscopic scale. And we learned that when we place soda water under a container with BTB, the BTB turns yellow, meaning that acid was made in the BTB. And that's exactly what happens when you add carbon dioxide to BTB by blowing in it. It turns from green to yellow because the BTB is turning acidic. So in the end, we concluded that the soda water was producing CO2, and that was floating through the air and then falling into the BTB, making it acidic. Which is great if we're just talking about the macroscopic scale, but we really want to zoom in and look at the nanoscopic scale. That means atoms and molecules. And that leads us straight to our goal for this video. We actually have just one, but it's kind of general. And our goal is to be able to use a chemical reaction to show what happens to atoms and molecules in the BTB when soda fizzes. So basically what this means, that we're learning about what atoms and molecules are doing at the nanoscopic scale, is that we're going to have to do a little bit of chemistry, which is really kind of exciting because chemistry is one of the best fields that we know that really allows us to explain what's really truly going on down at the deepest levels of reality. Now, probably the most important unit for understanding chemistry is the molecule, and a molecule is really just a group of atoms. And an atom is just the smallest amount of any element that you can have. They are indivisible. In fact, the word atom is just Greek for unable to be cut, because it's so hard to break atoms into smaller pieces. But anyways, what makes a group of atoms a molecule is that they are bonded together. So let's take a moment to look at some of the rules behind those bonds. Now there are actually lots of rules, and there's also lots of exceptions to those rules. We're going to keep it pretty simple here, but we did make a whole separate video that deals with molecular bonding, so you can go check that out if you want. At its most basic level, a bond is just when one atom sticks to another atom. And we'll usually see bonds represented as a stick between two atoms. One of the most important things to remember about bonding is that atoms in stable molecules will always form a specific number of chemical bonds. Hydrogen forms 1 bond, oxygen forms 2, and carbon will form 4 bonds. Now, not all atoms really get along. For instance, oxygen, if it has a choice, it will actually not bond with other oxygens. However, it bonds quite readily to carbon, and it will also bond readily with hydrogen. And that's part of the reason why there's so much CO2 and H2O in the universe. Oxygen bonds pretty easily with these elements. But let's get back to the point here. We want to know what's happening in the BTB as carbon dioxide is traveling through the air into that solution. In other words, what reaction is going on here? Now, to help us illustrate what's going on with this reaction, we're going to be using a molecular modeling kit. These are not super expensive. You can get one for $10 to $15 online. So let's start by considering the molecules that we were working with in our previous video. So the most important molecule that we saw was CO2, carbon dioxide. But don't forget that this was being added to water in the BTB. And the BTB turned yellow, which means that there was acid being produced. And just as a quick reminder, if you see these little numbers next to an element's symbol, that number is talking about the element to the left of it. So for instance, this 2 in CO2 is talking about the O, that's oxygen. So that means that CO2 is 1 carbon and 2 oxygens. So let's use some atoms from our molecular modeling kit to actually build these molecules. In carbon dioxide, we have our 1 carbon, which is black, and our 2 oxygens, which are red. And then we have our H2O, which means that there's 2 hydrogens and 1 oxygen. Now let's start with carbon dioxide and use our rules of molecular bonding to try to build this molecule. So each carbon will form 4 bonds. Let's go ahead and add those bonds to our atom. In this example, each bond is represented by a gray stick. So here we've added our 4 bonds to carbon, but we haven't created carbon dioxide yet. We have to figure out how to attach those 2 oxygens. Now don't forget that one of our rules of molecular bonding is that oxygen has to form 2 bonds. So let's attach our oxygens to the carbon. And we find that each oxygen only has 1 bond right now. There's only 1 gray stick attached. Well, if we change this around a little, we can take those extra bonds hanging off of the carbon and attach those to the oxygens. So here we see that each oxygen now has 2 bonds. Each one of those is called a double bond. And we can also represent this with a simple drawing, and this is what it looks like. A carbon double bonded to two oxygens. That's carbon dioxide. So now let's focus on our water molecule, H2O. We have one oxygen, and remember that each oxygen needs two bonds, but we have to figure out how to bond them to our hydrogens, the white atoms. So how are we going to do that? Well, let's start by taking some bonds and attaching them to the oxygen. There's our two bonds for oxygen. And from here it's actually pretty simple. Just attach each hydrogen to the oxygen because each hydrogen will form one bond. And there's our water molecule. And we can write this out also with an oxygen in the middle, single bonded to two hydrogens. That's our water. Now remember, the carbon dioxide and water are being added together, so let's make sure that we write that accordingly. Which still leaves us with our acid to deal with. But before we do that, we still have to remind you of a very, very important rule by which the universe operates. And that is that you cannot create or destroy matter. And what that means is that however many atoms you start with, you have to end with the same number of atoms and the same types of atoms. So what we're starting with here is one carbon, three oxygens, and two hydrogens. What that means is that what we end up with has to have the same number of each of those atoms. So here's our one carbon, followed by our three oxygens, and our two hydrogens. So now we have to follow our rules of molecular bonding to figure out what molecule these atoms are going to create. Well, let's start like we did last time, by putting 4 bonds on our carbon, since we know that carbon is going to form 4 bonds. Now there are actually a couple of ways to put this molecule together, but there's one way that best meets our molecular bonding rules, and that is to take each oxygen and bond them one time to the carbon at the center. But from there, remember, oxygen doesn't really want to bond with itself, but we can work around this problem by double bonding one of the oxygens to the carbon, and that just leaves each remaining oxygen with one more bond to fill, and so that's where our hydrogens are going to go, with a single bond each. So this molecule that we've just created is our mystery acid, and we call it carbonic acid because it's formed by combining carbon dioxide with water. Now before we go any further, we should remind ourselves about what a chemical reaction actually is. We have these molecules that we start with, we call these reactants, and these molecules are rearranging in order to form what we call the products. That's what we end with. So when the atoms in these molecules rearrange, what that really means is that bonds are breaking and reforming in order to create something new. So what I've done here is I've just rearranged the atoms in order to create our carbonic acid, which is the product. But here's where things can get even more interesting. This particular reaction is what's called a reversible reaction, and what that means is that our carbonic acid can actually rearrange again to reform the reactants. It can actually move backwards. And that is precisely what happens when you open a can of pop. There's a high concentration of carbonic acid dissolved in that solution. When you open the container and relieve the pressure, the carbonic acid rapidly reacts to form carbon dioxide gas and water. The carbon dioxide is where all the bubbles come from. And the point here is just to show that what we mean by a chemical reaction is that we have substances whose atoms rearrange by breaking and forming bonds to create new substances. Now there's one more way that we're going to illustrate this reaction, and we're going to call it a reaction table. No, not that kind of table. This is a table that will help us to mathematically analyze the numbers and types of atoms that are involved. So first, let's start over with our reactants and figure out how do we write out the formula for our product. Now remember, that was this carbonic acid. So let's go ahead and write out that formula. In the carbonic acid, we found 2 hydrogens, 1 carbon, and 3 oxygens. And that makes sense because those are the same numbers and types of atoms that we started with. The reactants on the left side of the arrow must have the same number of atoms as the products on the right side of the arrow. So let's put together our reaction table. So let's look at what we've done so far. So we've created a reactants side in green and a product side in pink. And we've indicated all the atoms we're going to deal with at the top: carbon, hydrogen, and oxygen. And on the sides of our table, we're going to place our molecules. So we have carbon dioxide and water as our reactants. And the very bottom row is for the total. On the right, we have our carbonic acid, and another row for the total. Let's go ahead and highlight our total in yellow. So the point of this table is to mathematically illustrate how the reactants and products compare mathematically. So let's go ahead and write in some numbers. Our carbon dioxide has 1 carbon. It's got 0 hydrogens, so we can put a 0 there. And it's got 2 oxygens. Now our water has got 0 carbons in it, so we can put a 0 there. There are 2 hydrogens, and then there's 1 oxygen. Now if we add up the totals and put them in the yellow boxes, what we find is that we have 1 carbon, because 1 plus 0 is 1, 2 hydrogens, because 0 plus 2 is 2, and 3 oxygens, because 2 plus 1 is 3. So that's the left side of our reaction table. The product side on the right is actually a lot easier because we only have 1 product. And in this product, we have 1 carbon, 2 hydrogens, and 3 oxygens. Now because there's only 1 product molecule, we don't really have to do any addition. That 1 molecule contains all the atoms that are in the products, so we can just bring those numbers down into the total. So with our reaction table, we have proven mathematically that the numbers and types of atoms that we started with are identical to the numbers and types of atoms that we ended with. So let's end by finishing off all the ways that we can represent this reaction. One way is to write out all of the molecular formulas. The other is to write them out in words. We can also build the molecules with our molecular kit. We can draw the molecular structures by showing their bonds and atoms. And finally, we can show everything mathematically with a reaction table. So now you should be able to explain at least a little bit of what's happening at the nanoscale. Let's review our goal to make sure that we met it. You should be able to use a chemical reaction to show what happens to atoms and molecules in the BTB when soda fizzes. If you don't think you can do this, go back and watch the parts of the video that you're not sure of. But remember, science is not just about answers, it's also about questions. So before we leave, go ahead and pause the video and see if you can come up with any questions that you still have about soda fizzing. Here's a few that we came up with. Why does a soda bottle only start fizzing after you open it? Are there any other gases that create acid when you dissolve them in water? And how strong is carbonic acid? How does it compare with other acids? See what else you can learn about what happens when soda fizzes. Until next time. Thank you.